Hey, welcome back. It's good to see some real faces. The topic today is to begin with a introduction to some central elements in statistics. This is something which we have been a little bit sloppy with. So when we now are running the Monte Carlo calculations, one of the things we have to live with is the fact that the random numbers, they are not independent stochastic variables. So they are generated by a pretty deterministic algorithm, which means that there can be correlations. So ideally, the random numbers which we generate when we are running a Monte Carlo calculation, they should be so-called independent and identically distributed. So identically distributed means that they follow the same probability distribution. So this could be a Gaussian, it could be a normal a uniform distribution, a student t distribution, or many of the other distributions. And they should be independent. That means that every single stochastic variable should not have any dependence on the other stochastic variables. That means if we compute a quantity, which is called the covariance, which we're going to define a little bit later today, and some of you have seen these things when you took the course in machine learning, because these resampling techniques, they are widely applied to basically all of science. So we have to live with the fact that our numbers will have some correlations. That means that there will be a bias in the calculation of specific quantities. But there's another thing which is a little bit deeper, which does not have anything to do with random numbers, because physical systems, they exhibit correlations, simply because you have interactions between particles. And the fact that you have interactions means that the systems will be correlated. So for those of you who may have seen models like the Ising model, this is a system which at the phase transition is a highly correlated system. And at the phase transition, a microscopic system where you have short-range interactions, they suddenly pervade the whole system, and you have long-range correlations. So a typical sign in these kind of systems of a second-order phase transitions is that you have something which is called a correlation distance, which goes to infinity. So this happens in statistical physics, but in quantum mechanical systems, there are correlations. So one thing is the ideal in a statistical calculation, where you want to have stochastic numbers which are not correlated. The other one are actually correlations which arise due to the underlying physics. What we are going to focus on are correlations within the data which do not have with physics. And since there will be some kind of correlations, it means also that the quantities which we will calculate, like the variance, which we then use to calculate a standard deviation, they may be influenced by the fact that there are correlations between the data points. So if we stick with a very, very simple definition of the variance with no correlations, we may actually calculate a standard deviation which is too optimistic. Too optimistic means too small. And these are the things which we're going to deal with, because in Monte Carlo calculations and in all calculations we deal with stochastic processes, if you cannot provide a standard deviation or an error estimate, nobody will accept your results. So you can look at this as a kind of, how to say, overarching view and take on what we are doing now, is that even if it's perhaps, it doesn't sound like the most exciting topic, it's actually a very important application of a statistical analysis on the data which we produce. So there are actually some, there's a video here on the bootstrap method, which is something which many of you may have encountered in machine learning. The bootstrap method is a widely used so-called resampling technique. So resampling simply means that you don't produce new data, but you use the same data to resample in this data set and then try to calculate as precisely as possible an estimate of the standard deviation. So typically in Monte Carlo calculations like those which we are doing, where you can generate zillions of Monte Carlo cycles and Monte Carlo estimates, a method which is widely used is called the blocking method. This is less used in statistical data analysis, where people tend to use a bootstrap method, which is typically applied on smaller data sets, where you typically have something from 100 to, let's say, 100,000 observations. But we, in a normal Monte Carlo calculation, we can produce millions and millions of expected values for the energy. And this is the thing which I wanted to give you the kind of top-down view on first, so you can see from the codes what we are going to implement, and then we're going to go through the mathematics. So if you want to see some inspiration, actually, this is Marius, who came across this idea while he was following this course, because we used an article written by two Danes on the blocking method, which didn't have enough rigorous mathematical proof of the convergence of the blocking method. So Marius was sitting there and listening to my dull lectures, and then he came across an idea, and that became a scientific article of 16 pages, which basically formed his thesis. And this is a more profound mathematical proof of the stability of the blocking method. So ideas pop up all the time, right? Okay, so I wanted to, there was a digression actually. I wanted to go back to the Jupyter notebook and take this kind of top-down approach first and look at what we are going to compute and what we need to have in our program. Now, this is a type of example which we would call a post-calculation analysis. So what does that mean? So a post-calculation analysis means that you run your heavy-duty Monte Carlo calculation, you produce the raw data, and then you do a statistical data analysis afterwards. So what we did last week was to discuss this gradient methods. And we're using these gradient methods because we want to save cycles. We don't want to waste cycles in order to find the optimal parameters at the minimum. But we just want to find this minimum by a gradient method. And the one which we normally recommend is either the simplest possible gradient method, or in this case, where you have few parameters, we can use these quasi-Newton methods after Broyden et al. And in the slides here, you will find what we normally call the top-down. So this is a kind of top-down view. So this contains a derivative of the wave function. This is still this 2-electron case, which I use as an example. If you take away the Coulomb interaction between the two electrons, you are actually back to the harmonic oscillator. So these are two electrons in a harmonic oscillator trap. And you can add an interaction or you can take it away. So it's pretty similar to the system you're doing. And in this case, we did some very few cycles. We did some 10,000s. And then we needed the derivative of the wave function. And here we calculate actually the derivative. We do a very brute force gradient descent where we have fixed a so-called step rate or learning rate, as we called it, or just step size, which is meant to replace the second derivative of the expected value of the energy. And in that case, what we saw then is that it's trying to find the optimal parameters. And you can see now after 50 iterations, this is the derivative with respect to one of the parameters, and this is with respect to the other. You will normally not get something which is exactly equal to 0. You will see, however, here that there is a kind of convergence in terms of the parameters, and your energy, which should be exactly equal to 3, is roughly, this energy value is roughly stabilizing around that value. So when you have these parameters, when you decide then that the number of iterations are okay, then you would take these two values for the variation of parameters, and you would start your large-scale Monte Carlo calculation. And that's the one you use to produce data. So the thing which comes next here is just a reminder of what was implemented. The other part of the code is this one which implements the Broyden-Fletcher-Gold-Fab Shannon algorithm. I think I did say it. I think I said it correctly. This is basically just a repetition of the previous code, except that now there is a dedicated function which calculates the energy derivative, these integrals, and it calculates the energy. And In this specific case, we are using this function, which comes with NumPy and SciPy, where you need to provide a function for the energy. This x0 is now your guess for the parameters. And in this case, I have two variational parameters, and I give a guess here, which is based roughly on my physics understanding of the system. And then I need also to provide a function which sets up the derivative. Now, when I've done that, the first thing here is that it produces now the parameters, and it has a final energy which is 3.01. And these are the optimal parameters in this case. So they might vary from time to time. So what you would end up doing is to find some kind of average of these parameters. So some people actually run a calculation with where they calculate the average of, let's say, 10 such runs, and then they use that one to make the big calculation. So there are many kind of sub-types of approaches which you can implement in these type of calculations. So the thing which, if you now go back to this function, you will see now that there's a statement after I run this, which is called printout true here. So I'm calling now with the optimal parameters. I'm now calling this with a large set of Monte Carlo cycles. And I will try to explain to you why the number of cycles is given by base 2. The reason for that is that this blocking method splits the data set in 2 each time. So I'm setting up a Monte Carlo run now with 2 to the 19th Monte Carlo cycles. So that's my big calculation. So the blocking method is a method which splits the data set. First, you have the full data set, then it splits it in 2. And then it tries to calculate the variance of these 2 data sets. Then it splits it in 2 again, and 2 again, and 2 again, and 2 again, till you have the smallest possible data set. And the whole idea is to see whether this variance stabilizes as a function of the block size. And if the block size, if it reaches a certain limit, then that is the minimum block size for independent stochastic variables. So that's the basic overarching kind of message which we have here. So if you look back at this function, what I'm doing now is actually to print here the local energy or the contribution to the local energy at each Monte Carlo cycle. So this becomes a pretty large file. So this file is going to have 2 to the 19th data points. You can make this smaller by printing out every 100 Monte Carlo cycles. That's also fully possible. Running this in parallel, what you would typically do then is to write to different files. And then in the post-analysis, you would read in the energy from the different files. But this has now 2 to the 19th energy entries. So just expectation values of the energy. I'm not calculating the energy squared. I'm just calculating the energy. This is used to calculate the mean value. And when I have this mean value, I'm going to calculate the variance, and I'm going to calculate the covariance. So these are the statistical quantities which we are going to calculate now. So the blocking method is actually and bootstrapping as well. They are cheap ways of estimating the covariance. The covariance is a measure of the degree of correlations between each observation you have. So ideally, the covariance should be equal to 0. So the total variance is given by the variance of an ideal experiment plus the covariance, which measures the degree of correlations between different experiments. So if our results are independent and identically distributed, the covariance should be equal to 0. The covariance involves a double sum. So if you want to calculate the covariance in your Monte Carlo calculation, if you now look at the number over cycles here, if this is 2 to the 19th, you would need a double loop over 2 to the 19th. And you don't want to do that. Or even, this is something you can try out. Even if you now have 2 to the 19th numbers, try to calculate the covariance by making a double loop over 2 to the 19th. If you get to 2 to 10,000, it's going to be okay. If you go to 100,000, it's going to be pretty slow. When you go to 2 to the 19th, you can just go for a nap and come back the day after and get your result. So even if you have the data points, running a double loop over that is something which is going to be time consuming. So if you know, if the kind of basic message is that these methods are cheap ways of estimating the covariance. The blocking method, you can show that that converges towards the correct variance. So what you will need, I'm just pointing to the things you need to have in your program. So in your program, when you now have done the gradient descent and all that machinery, is to have a printout statement. That shouldn't be that difficult. And then you would write that to file. When you've written that to file, you are free to use the functions which we have here. So there's one function which does the bootstrapping, which I'm going to explain to you how functions. So you can run that one. And this bootstrapping here produces the mean value should not change. So the mean value, which you calculated up here, 3.96 something, that stays the same irrespective of method. And you will see that when I do the bootstrapping, I'm coming back to what it means, but you could actually take these functions and just use them for the post analysis. If you have a file which simply contains the output from your code. So you can obviously write your own bootstrap analysis or blocking analysis. There is nothing which hinders you that, but feel free to use these codes for the post analysis. These methods are not very complicated to program yourself. And for those of you who took the machine learning course, you actually programmed the bootstrapping method. So you could reuse your own codes from that. So this gives an estimate of the standard deviation. And we are going later to have a kind of critical discussion of what it actually means. And then there is another function, and this is the one which is taken from Mario's article here. And this does the bootstrapping, now the blocking, and the standard deviation is a little bit different, but you see the mean value is the same. So when you are going to present these numbers, if you are going back home and you want to impress family with these numbers, then you should say my results are 3.01 plus minus 0.011. These are the numbers you should present. So from the kind of top-down approach, which we take now, it means that you need a statement when you're running the big Monte Carlo calculation, where you actually introduce this printout of the data, which in your case is just the energy measured at each Monte Carlo cycle. That becomes an observable. Some people try to save space and they just print every 100 value, hoping that then the correlations will be smaller. And then when you have that, then you have a post analysis and you make the relevant plots and so on. So what I want to do now is actually to give you first some kind of overarching view on why we do the resampling methods. One of the reasons why we do them is that in many cases, you cannot rerun the experiments. In these Monte Carlo calculations, we are in a fortunate situation where we can run these experiments again and again and again. And they're not that time expensive when it comes to CPU cycles. But if you're running a real experiment, it's not given that they will let you run a new experiment again if you want more data. So if you're doing particle physics, a typical experiment at CERN runs for half a year. And if you think of just the electricity bill for that, that's a non-negligible price tag. So an experiment at CERN is, there's a reason why CERN closes wintertime, because that's when the electricity price is at its highest. They go down for maintenance. So there are cases like our cases where we can just generate data, but then in many instances, you cannot regenerate data. And you have to be happy with what you have. So let me just go back to the slides then, and then take a quick look at the more overarching things, and then we jump back to the whiteboard here. So these resamplings methods, so if you look at our simulations, you should always think of them as computer experiments. Actually, your data will change from experiment to experiment because you're starting with a different random number. And even if you did that, it did not do that, depending on the temperature and how your laptop is functioning or your machine is functioning, you may get slightly different results from each experiment. That can happen because your laptop is like an experimental device, or your high-performance computing facility which you're running on. The results which you have then, they can then be treated with the same statistical analysis tools as you would analyze experimental data. So when you do an experimental analysis, you would run that in the same way as we are running the analysis of our theoretical calculations. And in all experiments, you want an expectation value, and you want to estimate how accurate they are, and you want to find the possible sources for errors. Now, if you look at errors, there are basically two types of errors: the statistical ones, and these are those which we can estimate, and then we have systematical ones. So if you think of what we are doing here, what kind of systematical errors could you think of if you look at the calculations we are running?
Any good ideas, suggestions?
The precision, the representation.
That could be one. What other types of systematical errors could we think of?
The bias, because of the way the numbers are generated, the bias.
They could also enter the statistical errors, actually. You can actually measure that. But if you think of this system we have set up, if you, in this case, we are trying to model bosons with a specific type of trap and a specific type of interaction.
The guess function.
Yeah, but also the Hamiltonian itself. So the Hamiltonian is just a guess we made because we have some physics insight, but it doesn't need to be the correct Hamiltonian. So the trial wave function introduces a systematic error. And these are, but you could say now that with the trial wave function, when you do the calculations of the integrals, given a given Hamiltonian, then you can calculate the integrals and give an error in the integrals using statistics tools. But your Hamiltonian has an error which we don't know because it's an assumption we made. So we don't have a good enough theory for that Hamiltonian. So that means that to quantify the systematic error in the Hamiltonian we make and the way we describe the system is something which is very difficult. So you could say that the way you could define it is to compare with experiment. And if there's a large deviation from experiment, and if you believe your theoretical method, if you really believe that what you're doing is correct, when you run the calculation, and that the energies are the best you can get, then clearly if you have a big deviation, that means that your Hamiltonian is wrong. So systematic errors are the bad ones. They are often difficult to quantify properly. And this is something in many cases we have to live with. You will often see in science articles, scientific articles, you will see a good evaluation of the statistical error because we have tools to do that. But you would often see a very sloppy or non-existent analysis of the statistical of this systematic error. So they are typically method specific also.
Okay, so let's continue a little bit. And one of the things I'm going, you can go through some of the slides here, but I wanted now to actually switch to the whiteboard and slow down the pace a little bit. Let's do that. Can you see well? Yeah, seems okay. Okay, good. So there are some basic elements which we need here. So in the statistical analysis, or what we normally call the statistical errors, there are some minor ingredients, or several ingredients actually, not minor ingredients, but several small ingredients, which I'm going to remind you of. And I know that many of you have taken computational physics, and some of you have taken a course in machine learning, and probably you've seen these things here and there, but I'm going to take the liberty of repeating them because they are important for the analysis and the understanding of these resampling techniques. So what we want is obviously to calculate the expected values. So we are going to calculate something like and if we now think of x or a function f of x, so this is the expected value of that function. We know that if we have a discrete probability, then we would have some p of x multiplied with a function f of x and d of x. So this is the quantity which we want. This quantity is going to have fluctuations around the mean value, and specific distributions have specific fluctuations. We know that the normal distribution has a width, which we call the standard deviation, and that's given by the square root of the variance. So if we look at the other quantities which we can easily calculate, so we can calculate things like the moments, so we can have to the power of n, and this is given by a similar integral. And then we have p of x, f squared of x, n, sorry, this should be an n here. And then we know that the variance of this function f of x, and I'm going to use a notation which is given by sigma squared, and sometimes I'm going to put a subscript f, but in many cases I'm just going to skip the subscript. And this quantity here is given then by the expected value of the function squared. So this simply measures the deviation from the mean value. And this is given by the expected value of the function f of x. And this is then squared. And as an integral, this will simply be given by x in the domain where it's defined, p of x. And then I would simply have f of x minus the mean value, mu of f, squared of d of x. And in this specific, in the notation which I'm going to use, then I'm going to define this as a mu of f. So that's the mean value. These are the typical quantities which we want to evaluate. Our problem is that if we want to evaluate this one, we have to evaluate the integral in terms of a Monte Carlo integral. In our case, this is now given by 1 over the number of Monte Carlo cycles of I equal 1 up to n. And then we have f of x of I minus this mu of f. And now I'm going to put a bar on top of it to indicate that this is not the correct mean value. It's actually an approximation which we are making, which is the mean value of the sample. So in the literature, what you will find is that this is called the sample variance. So this is the whole sample of data which you have. So this would be the sample variance. And this quantity here is then the sample mean. And we are obviously hoping that we can invoke the law of large numbers, and in the limit where m goes infinity, that this sample mean value approaches the true mean value. But in general, what we have to live with is that this sample mean is different from the true mean value. And similarly, if we now call the sample variance, so we could call that one for sigma bar of f. We also have that sigma bar of f is different from the true variance of f. So the question is now, how can we estimate these quantities correctly? If we go back a little bit, we also have, so let's just remind ourselves about some other important quantities when we do statistics. So one of the, just wanted to find my cheat sheet again here. There's a very important limit theorem when we do statistics. And we are going to use this theorem to introduce these resampling methods as well. I know that some of you are familiar with the central limit theorem. Does that ring a bell? Have you seen the proof of it? I see them online. So let me just repeat that one because that's an important theorem, okay? So we have something now which is called the central limit theorem, which is going to play an important role when we are setting up the proper estimation of the variance. So ideally, what we want is to have this quantity here, or something which is pretty close. When you take the square root of that quantity, that should correspond to your standard deviation. And that's the error you want to list when you want to present your data. So an important theorem in statistics is called the central limit theorem. So let me just present that to you. And we are going to see how that functions in connection with the bootstrap and the blocking methods. So you can get a kind of intuitive understanding of what these methods are doing. So the way I'm going to do now is I'm going to link the central limit theorem with these resampling techniques. So then we will illustrate the central limit theorem and how it functions when we resample the data set. So the central limit theorem simply states that if you have identically distributed and independent variables, so let me just introduce that. So that is independent and identically distributed variables. Distributed stochastic variables. What the central limit says is that if this is the case, then if X is now a stochastic variable, which belongs to this class of stochastic events, then in the limit, where this M goes to infinity, the distribution of the variables is going to be a normal distribution or Gaussian, if it has a specific variance and a mean value which is different from 0. So then the final distribution, the final probability distribution, PDF, is going to be a Gaussian. This is not true for all initial distributions. So you start with an initial distribution, and if the central limit theorem applies, then the distribution of all the events when M goes and becomes infinitely large should approach a Gaussian. So what does that mean? So suppose now that you have a variable X which follows a specific distribution given by a P of X. So there's a distribution P of X, which now X follows. That means that a specific variable X, if we now, the mean value of that one, which we often write like this, mu of X, and now for simplicity, I'm just going to write this as mu. And if the distribution is a continuous one, this is going to be given by P of X times X or D of X. If it's not a continuous distribution, this is just going to be a sum over I equal 1 up to n, the number of events which we have, p of x of I multiplied with x of I. That's in case we have a discrete probability distribution, just a discrete probability. Okay. In this case, so when you approach this with a division by n, this is because what you're assuming then is that your probability is now represented. You don't know the probability distribution. And then you do the sample mean, and you're assuming that all your events have the same probability. So what you're hoping for then, invoking the central limit theorem, that in the limit m goes to infinity, that you're approaching the correct mean value. So this is actually what you do in a real calculation. You're calculating this quantity here. So you can read that as your probability being approximated with the uniform distribution. And then every event has the same likelihood. Okay, so the thing which we want to calculate, what we want to show now, suppose now we define a new set of variables, and this x here is now the result of a given experiment which we run. You could now think of this x, so we have an experiment. Which you could call for an experiment xi. This is let's call it x alpha. And this x alpha has a mean value, which is given by 1. And now I'm just putting this as a 1 over n. And you have a sum of I equal 1 up to n. And this is your experiment, which you're running here. In principle, what you would like to calculate, if you know the distribution, since we now have assumed that we know the distribution, this should be p of x, x of I. Alternatively, we just have x, p of x, d of x. So suppose now we are running an experiment every evening. So this is evening alpha. And then you have an evening beta. Oh, okay. Let me just take this one away here. Okay. Sorry. So this evening alpha, we run an experiment. And then we just rerun it. So it means that we have a set of samples for every experiment. So it means that we are going to have a new variable. So suppose we run these types of experiments many, many times. So that means that we have a new variable, which I'm going to call for z, which is now going to be the sum over all these individual experiments. So that's the mean value. So the total mean value. So this is also mean value. X, we have x1 bar plus x2 bar plus x2, x3. And this is something which we are going to do m times. So this could be one of your spare time activities where you run such experiments in n evenings. I guess you don't have anything to do in the evenings. So this is a new variable. Now the question we make, we know that the x's, so these x of i's, are given by p of x. And we know that each single one is independent and identically distributed. So the question we answer now, so we put a bar on top here, what is the distribution which describes or governs, which describes Z? So can we find that distribution? Now, the central limit theorem claims that that distribution is a Gaussian. So let's prove that. So keep now in mind, we have an underlying distribution for the x's, and the x's are independent of each other and identically distributed with this p of x. And then we ask you the question now, when we bring all these together, what is the final distribution? This has actually important consequences for the way we are going to estimate the error. Because this is going to lead to something which has a covariance, which is equal to 0, simply because we are assuming that the events are identically distributed and independent of each other. So what we're going to do now is simply to do some changes. So I'm going to let Z with a bar on top just become Z. And then I'm going to make, just for the sake of simplicity, so an X of alpha here is just going to go over to an X of alpha, just for simplicity. So in principle, this Z is now, if we now look at the mean value here, this is going to be given as a sum over n, and then we have a sum over alpha equal to 1 up to n, and this has the single experiments, x bar alpha, and this is again the same as, this is just for the sake of completeness, 1 over n, and we're going to pick this up a little bit later. So we have an alpha I equal 1 to n, and then we have an alpha equal 1 up to n, and we have an x of I here. So it's the mean value over all the mean values. So this quantity is conserved. It doesn't change. So let's now look at the definition or the calculation of this new probability P of Z. And the way we're going to construct this is the product of all this dx1. We have a px1. So these are the same probabilities, dx2 of px2. And this goes all the way up to a dxm of p of xm. And this is multiplied with a delta function, where we have put a constraint that the probability is now the product of all the single probability, with a constraint that the mean value, z, is given by the mean value of all the single x's. So this is the constraint which we are putting on the probability P of Z. Normally, when you have all these small events, the normal way you would have put it is that P of Z would simply be P of x1, x2, up to xm. And that will be given by the products of P of x1, D of x1, and all the way up to P of xm of D of xm. So that's the standard approximation we would have used, but now we're putting the constraint that the mean value has to be equal to the mean value of all the single x's. And the way we now can proceed is to use this more compact representation of the delta function. And you know that you have the delta function now can be given, so this delta z minus x1 plus x2 plus x of m divided by m. We can use the definitions of the delta function in terms of an exponential. So this runs from minus infinity to plus infinity. There's a dq, there is a e of iq. This sounds like a complication, but it's actually going to simplify things. And then it has x1 plus x2 and all the way up to xm divided by m, like that. So I can now insert that one in the definition for the probability. So it means that if I plug that one into this probability of z, what I get then is 1 divided by 2 pi, and then I have an integral from minus infinity to plus infinity, the exponential here of iq. And then remember now that I defined this variable x, this mean value, and let me just bring that back again. I'm going to call this one, since these are identical experiments, I'm just going to label this as a mu here for each single one of these. So this is going to be given by a z minus mu, and I have an integral over dq. And this is again multiplied with a new integral over x, minus infinity, plus infinity, and then I have a d of x, p of x, and then I have the exponential, and then I have an iq of mu minus x divided by m, and this is now to the power of m. So it's not so difficult to see that that's actually what happens. So what we need to look at now is this specific integral, because this is something which we can actually calculate. And this is the one which is going to lead to the Gaussian distribution. But I see we are a little bit over time now. So let's just pause the recording. When you do this kind of hybrid teaching, there are so many more different things you have to think of. And what I realize is normally when I teach, I want to use a whiteboard or a blackboard. You walk around and you wave your hands, and it becomes a little bit more monotonic when you teach like this, because you're a little bit more focused on all the small things. I normally walk around. That's because my brain is connected to my legs. Okay. Let's now look at this specific integral which we have. So we are going to take a closer look at this integral which we have here, this part. So let's analyze that one and see what we can do here. Over d of x, that's a p of x. And then we have the exp y of q. So we just take one of them, mu minus x, divided by m. So let's just analyze this piece. Now, if you look at that one, this is something which we can Taylor expand. So we take the exponential and just simply Taylor expand, and then you will see that there are things which just fall out almost automatically here. So we have a 1 plus an I of q of mu minus x divided by m. And then we get that minus a q squared of mu minus x squared divided by m squared and plus plus. So these are the high order terms. So if you now think back to some of the quantities which we have defined already, so we're assuming that the probability has been normalized. So that should be equal to minus to 1. We are also assuming that the mean value is given by this quantity dx, p of x times x. So these are some quantities which we already have defined. So if you now look at the integral which we have to evaluate, what would the first term give us then?
1.
Just 1. Bravo. So it's equal to 1. If you look at the second term, what would you expect then? Right. Wow. That's 0. And that's simply because we have the mean value already, and then we subtract the mean value. So this mu is just a constant, and then we have x. So this should just be, and if you now look at the second value, what would you expect from that one? So we have a q squared. That's the variance. Because remember now that the variance for this specific quantity here is given by p of x, and then I have a dx, and then I have x minus mu squared. That's the definition of the variance. So the third term here is actually the variance. So we get minus sigma squared of m squared, and then we have some high order terms here. Now what we're going to do then is to neglect the high order terms and simply look at the following. So what we're going to say now is that this integral, which we had over all the m's, since these are identically distributed variables, p of x, and then we have an exponential, and then we have our IQ of mu minus x divided by n. So what we can do now is simply to approximate this with the first two terms, 1 minus, and then you have a q squared, sigma squared, divided by 2 of m squared to the power of n. So we simply leave out the high order term. By the way, there should be a factor of 2 here. This is a Taylor expansion. Sorry, forgot that. So the result then, if we now take in the limit, you can actually show that when you evaluate this integral, in the limit m becomes large, then you can show that this probability, when you calculate, when you now insert this quantity back into the full integral, so, and where the full integral actually also includes this piece. So this is a little bit more elaborate integral to make, so I'm just stating the final result. So what you end up with then is an integral for, or a probability distribution for this P of z, which is given by 2 pi of sigma squared divided by n. And this is multiplied with the exponential of minus z minus mu squared divided by 2. And I'm just going to put this one in a, rewrite this in a slightly different way of m's like this. So this is nothing but a Gaussian with mean value of mu. So the mean value is the same as the mean value of all the single experiments. So I'm simply taking the mean value of all the simple of the, because remember that the z here is given by the mean value of all the single experiments, x1 bar plus x2 bar up to xn divided by n. And we assume that each of them is equal to n to mu. So this is just simply n times mu divided by m. So the mean value is simply this mu here. So what we have now is a new distribution. So new distribution which is a Gaussian. With mean value equal to mu and variance, which is equal sigma squared divided by m. In our previous case, when we started, the variance was actually given by sigma squared, the variance of each single experiment. So remember now that the variance of each single experiment, which contains a given number of observations. So each single experiment has a certain number of observations. So the variance of x is sigma squared, because we had that sigma squared was defined as p of x minus mu squared of d of x. So that's the sigma squared is the variance for each single experiment. What I'm doing now is I'm making a huge set of experiments, and I'm asking myself, what is the final distribution of all these experiments? So the final distribution is a Gaussian, but which has a variance, which is given by sigma squared divided by the total number of experiments we have made. So that means that when you now make an experiment and you repeat this again and again and again and again, what you should see then is something which approaches this sigma squared here, divided by m. So let's see if that is the case. So what I'm going to do now is to run some experiments, but I'm going to use that to catch two birds with a stone. I'm going to use that to introduce the bootstrap method first. And I'm going to apply the bootstrap method to actually show the central limit theorem. I don't need to do that. I could actually generate new normal distributions again and again and again. But I'm going to use this as a kind of intermediate step to show the bootstrap method first. So the bootstrap method is a resampling technique, which is extremely simple. So that's a resampling method. So what you do in that case, you have a data set now. So your data set X contains all these observations you've made, and each one of these can be thought of as a stochastic variable. So you have an X1, you have an X2, X3. So these are different numbers. These do not need to be the mean values which we defined earlier. So these are just a specific number of observations we have made. And we are assuming that these X of i's are identically distributed, and there is some PDF probability distribution which defines these, or which these numbers actually follow. So I have a probability distribution, and from that I can generate each X with a given probability. Now, what you are doing then in the bootstrap method, so this is your X, and in the bootstrap, what you end up doing is the following. You draw a so-called new sample. So let's just set up the algorithm. You would draw a so-called bootstrap sample. And let's call this for X1. That's the first one we do. And that gives us now observations, X1 star. There is an X2 star, up to an XN star. Now, the thing is that when we do this bootstrap, and this is in Norwegian, it's called utvalg ved tilbakelegging. So you're actually bringing back. It means that what you can actually do then is to pick the same number again, or the same X again. So these X1s, this XI star, can be the same numbers. So because you can, when you now pick one, then you bring it back again. And that means that when you pick it randomly, so you're picking randomly in the first table, can be the same, picked randomly. Randomly from the original X. And this original X is the quantity which we have here. So it means that these numbers could be the same actually. You can actually show this mathematically. It's going to converge to the correct standard deviation and the correct variance. So we are not going to go through the proof actually. Then you would repeat this step. So this was the first one, as many times as you want. So that means that you would now provide new data sets each time. So for each new data set, you would calculate the mean value and you would calculate the variance. So you can now think of these X1s as your new data set. And then you repeat it B times. And that's going to yield some estimate for the mean value. So each time you do that, you should get an estimate for the mean value and perhaps also the variance. And compute estimates for the variance for various expected values. So this could be the variance which you're interested in, or it could be the mean value which you're interested in, and so on. So a typical one which you end up calculating is actually the variance. Then your final variance is going to be the mean value of all these variances. So that means, so suppose now that we estimate, suppose now that at each time, so let me just rewrite this one. At each time we produce, oops, what I'm doing here, I can't write correctly here. Each time we have an estimate. Suppose we are looking at the mean value, for instance. Let's call this a mu of B, and we are just going to put this a number here. So I'm just going to call this a B of J, for instance. This is just experiment J. Then, when we are done with that, when we're done with all these kind of computations of, let's say, the mean value, what we will do next is to compute, finally, when we're done with that, for instance, the mean value of mu, which would then be given by 1 over B here, the total number of times we have produced a new data set. And so let's call this a mu of beta J. And then you would calculate the variance and the standard deviation. So if we want the standard deviation then, and let's just call that STD, that would be something like the square root of the variance. So it'd be 1 over B, and then I would have a sum over J equal 1. So this should be a sum over J actually. J equal 1 up to the total number which we have. And then we would have this mu of Bj minus mu squared. So that could be one typical quantity which you could calculate. So the whole thing now is that what you're doing is that every time you are producing a new data set, and you think of that as your data set, and you compute different expected values based on that. Then at the end, yeah.
You can finish what you're saying, then I ask a question.
Okay. Okay. So
by using the same data sets, you reshuffle randomly. You can pick the same numbers. And then each time you do this, you calculate the expected values you are interested in. So in our case, this, for instance, could be the mean value. And then with that mean value, we can calculate the variance in that mean value. Yeah.
Shouldn't we take the variance of each bootstrap cycle and do the mean of each variance?
See, that is if you're looking after the variance as a kind of estimator. So when I put up the mean value here, that would be the mean value I'm looking after. And then you could think of calculating the variance as another quantity. So you can decide which quantity you're looking after, right? So this was just an example which I picked here. So I said here for various expected values, it could be the variance, it could be the mean value, or it could be a higher powered momentum. So what I wanted to show you now is an example. So keep in mind this extremely simple recipe. And then if you now go back to the central limit theorem, so the central limit theorem says now that we have a variance for each single experiment. And then when I repeat this, my variance should actually decrease by 1 over n, which is the total number of experiments which I'm running. So if I believe in the central limit theorem, I could now run an experiment where I use a bootstrap. However, what I could have done, instead of now resampling the data the way I'm doing it here, I could now just generate a new data set using the normal distribution. So there are different ways of doing that. If it's cheap and easy to do that, you don't need to do bootstrapping. So the example which I'm going to show you now is a very simple case, but it demonstrates the central limit theorem. So let me explain the example first, and then we're going to look at what it looks like when we run it. So I'm going to take a Gaussian with an initial Gaussian with an initial value of mu, with mu as a mean value, and a given variance sigma squared. So one thing I could do, so I produce something like n equal 10,000 numbers, which are distributed according to the normal distribution with this given mean and variance. So that gives me my x, which is now going to contain random numbers from x1, x2, up to x 10,000. Now, one thing I could do is simply to generate a new data set. So I could call this y, and that could be the same random numbers generated by the same distribution. So I could have a y1, y2, up to y 10,000. This would be a new distribution. And then I could repeat this now 10,000 times, just to give you an example, by simply calling the normal distribution. This is very fast. So I would just make 10,000 new data sets by just calling the normal distribution. And each data set has 10,000 entries. Okay? So I would have 10 to the power of 8 random numbers, which I've generated. But I could now think of each one as something which I have generated by calling the normal distribution. Computationally, this is extremely fast. And this is the way you would typically do it if you want to prove numerically the central limit theorem. So I'm saying prove numerically because you have numerical proofs, which you can do on the same footing as standard paper and pencil theorems. But the other thing you could do now, so this would be one possible way, or use Bootstrap. And now I'm going to call this m times on x equal this data set, x1, x2, up to x 10,000. So I could produce now, if m is equal to 10,000, I could do the bootstrapping 10,000 times by just picking numbers randomly in this data set by replacing every time. So there are different approaches. Now, the reason why we introduce Bootstrap is that if you look at your Monte Carlo calculation, this is not something you would like to rerun 10,000 times. So if you have a large run, it's not given that you will get more CPU times to run it again. So you have a limit. Normally when you apply for CPU time, you get something like 1 million to 2 million CPU hours per year or per semester. And that's what you have. So clearly, if you've made a run, then if you want to do this kind of statistical analysis, you would typically use Bootstrap. Many experiments have less than 10,000 entries. If you're making surveys with interviewing people, this is really time consuming. And if you have 1,000 people, then clearly that's your data set. So there's always, if we look at this simple example you see now, doing a bootstrap is actually a kind of overkill. You could actually just call a random number generator again and again and again. But let's take a look at the code, which we can then set up and run these calculations with. And some of you have seen this before. So so what I'm doing here now, let's just bring that one. So there is an example here of the application of the central limit theorem. So the things which you saw in the slides are also the things which you will see in the Jupyter notebook here. So in this particular case, this code here does the bootstrapping. So if you look at what I have here, I have a mean value of 100, and I have a sigma, which is put to 15. So sigma is the square root of the standard deviation. No, of the variance, sorry. And then I do 10,000 data points. And then I say that my x is simply the mean value plus the sigma times the random numbers which are generated by the normal distribution. So this is around n. So what I'm doing here is I'm setting up 10,000 data points, which are generated according to the normal distribution with a mean value of 100 and a standard deviation of 15. Then I have a bootstrap here. So this bootstrap transfers this data set. And in this particular case, what I've done is that I put the number of bootstraps operations equal to the number of data points. So many people often set that as the upper limit when you do a bootstrapping. And then when I'm doing this now, I'm simply reshuffling the data. So I pick randomly an integer between the data set which I have, and I allow all the integers to be, all the data sets to be present here. And then I calculate the mean value for each one of these. So this randint here, random randint, this is my reshuffle total data set. And there you see now that what I'm computing here is actually the mean value. So by doing this reshuffling, as you can see here, the mean value should not change. This is the original. This is my new one. So they shouldn't change. This is my original standard deviation. So when I only have 10,000 samples, I will not get 15 because I have a limited number of data points. So if I were to increase this to 100,000, then I would get something which is closer to 15. So this you already see a limitation of you calling a random number generator, which you have specified, should give a standard deviation of 15, not giving you 15. Okay? So this is something we have to live with because you have few data points. Then what you see here is actually my bootstrapped standard deviation. And this should be 15 divided by the square root of 10,000, which is 100. And this is what you see here. So what you will also see when you, so this is a demonstration of using bootstrap in order to test the central limit theorem. Now, if you want to plot this as a histogram, what you see now is that in this case, it's almost around 100, but it's a little bit skewed. This tells you simply that you're not, since you have a random numbers, which a generator, which also has some correlations in it, and you're only producing 10,000 numbers, you don't get an exact normal distribution centered around 100. And then, but what you see now is it looks like a Gaussian, right? But it's a little bit skewed, and that's simply also reflected in your standard deviation. So this is actually not 100, but it's 99.9. It should have been 100. This also comes back to what we discussed previously, that when you do the sample mean, this is a sample mean, you don't get the exact mean value. So this is a clear demonstration that ideally I should get 100, but I don't get it. If I were to increase the numbers here, or the calculate this one, I should get closer to, but this is going to take more time. And now you clearly see that when I run it for 10,000, it was like this. Now I'm doing 100,000 bootstraps. So this is going to take a little bit more time. And you will see that it actually does take a little bit more time here. So we can just wait a little bit. And perhaps you guys have some questions about what we are doing here, things which are unclear. But the main message is that if you produce a set of random numbers, even if you have defined the normal distribution and everything, when you look at your results are given by the sample mean. And that does not need to be exactly equal to what you specified here, because you have a sample of data points. So when you clearly increase the number of data points, this is going to get closer and closer to the correct value. And what you will also see then is that your standard deviation is going to diminish. When you see now you were a little bit better off here, and you see also the mean value now is actually getting closer to 100. This is now your new standard deviation, which is the square root of 100,000. And if you plot the histogram, so if you just keep this in mind, which was a little bit more, how to say, a little bit more choppy, what you should get now is actually a better distribution of the numbers, and it looks much smoother, right? So you see clearly the application of the law of large numbers and the action of the central limit theorem. So these are many of the things which we base the coming analysis on. There's one thing which I actually am going to bring up with the slides before we go back to the, yeah?
First, we had a standard deviation of 15,
Yeah.
and after it was much lower than that.
Yeah.
Isn't that just
No, because what I'm doing now,
introduce a new distribution. So if you go back to the notes which we did with the central limit theorem, I'm not producing 100,000 new samples. So what I'm doing, I have 100,000, which is my starting point. I do my bootstrapping, and in each, I do this 100,000 times. So that means that I have now 10 to the 10th numbers.
okay, yeah, okay, yeah.
So that's what I did when I did the bootstrapping here. And the new distribution, if we now follow the central limit theorem, this is where you started. But the new distribution with now 10 to the 10 numbers should have the same mean value. That shouldn't change. But I have reduced the variance and the standard deviation by the square root of the number of bootstraps I made or experiments I made.
So, for example, the standard deviation in our calculations would be the standard deviation given by the bootstrap times the number of samples, but not the standard deviation given by bootstrap alone. Right?
No, right,
Yeah.
right,
Okay.
exactly. So these are some small things which it takes some time to digest all of them. So that's why it's so important to think of the central limit theorem, because essentially what you're doing now is to try to implement the central limit theorem. And you could now think, when you run things in parallel, you could now think of every calculation you run on a node. If you have 100 nodes, you could then think of you having 100 experiments. Here we did it 100,000s of times, since we did 100,000 bootstraps. But you can actually think of this as you doing a set of experiments on each parallel node, and each one of them represents, let's say, 1 million Monte Carlo cycles. And if you do this 100 times, you have 100 experiments with 1 million Monte Carlo cycles. And your standard deviation should then be the standard deviation of each experiment with a 1 million divided by the square root of 100. That's the number you should approach, if you believe in the central limit theorem, and if that applies. But remember again that the central limit theorem has as a basis stochastic events which are independent and identically distributed. That's a very important assumption which is made in order to derive the central limit theorem. So I hope this simple example is now going to let us move on to the next topic, which is the actual calculation of the variance and the standard deviation. And that means that we need to look at another quantity, because this algorithm, which I call the blocking algorithm, is based on the quantity called the covariance. And this is something you may have seen, so I'm just taking the liberty of repeating. You will find many of the things which we discussed in the previous lecture, also in the slides here. So these are the typical moments, the mean value and so on. Now, there is a quantity, again, this is the variance, but the quantity which we are interested in is something which is called the covariance. So if you have independent and identically distributed events, the covariance is exactly equal to 0. So that means that there is not going to be any contribution from this term to the total variance of the data set which we have. In case we have that, then we need to evaluate this quantity. And if you look at this quantity here, when you translate that into discrete events, this will be represented by a double sum. And you don't want to evaluate a double sum over 1 million Monte Carlo cycles. Or if you do 1 billion, you really want to avoid that. So these techniques like bootstrap and blocking, what they're actually aiming at, since we know that there will be correlations due to the random numbers we have constructed, we are going to see that we want actually to calculate or have an approximation for this quantity which is reliable. And this is where methods like blocking and bootstrap come in. Okay, so there are some more manipulations here which I invite you to take a look at. And in our case, what happens then is that in case the numbers are independent and identically distributed, these two terms will cancel each other. So there are some other things here, but what I want to do now is to go back to the whiteboard. And I wanted to bring up the definitions of quantities which we need in order to discuss the blocking method. So in many of these calculations, people actually end up using the blocking method because that's better suited for huge data sets. So when we did the few data sets which we had previously, then we could get away with bootstrap. So why is it not showing up? There it comes, yeah. It actually died out. Okay, so let's bring up some further definitions here. And I'm going to define the blocking method. And there are some definitions which we need to set up. So we will probably continue with this in next week. So I will use parts of next week to wrap up the discussion on the blocking method because I see we are almost running a little bit out of time here. So I see we have, why don't we wait till next time? Is that okay? We have only 4 minutes left here. And it's a little bit stupid to just start with something new when we only have 4 minutes left, if that's okay with everybody. It's not because I want to give you 4 minutes extra, but no. Now let's take this. So next week I'm going to derive this blocking method. But the important things to keep in mind is that the reason we use this is that we want to have a reliable estimate of the standard deviation without having to calculate the covariance. The covariance is a double loop computationally. And the blocking method is actually a method which allows you to compute this one reliably. And you can prove that it actually approaches the correct standard deviation. And it's a very powerful method. Okay, I'm going to stop the recording.